This question is from GATE Mechanical Engineering paper of 2019. This is question number 47 of set 1. The question is, three slabs are joined together as shown in the figure. So there is a figure below in which it is shown that three slabs are joined. There is no thermal contact resistance at the interface. The center slab experiences a non-uniform internal heat generation with an average value equal to 10,000 watt per meter cube, while the left and right slabs have no internal heat generation. All slabs have thickness equal to 1 meter and the thermal conductivity of each slab is equal to 5 watt per meter per Kelvin. The two extreme faces are exposed to fluids with heat transfer coefficient of 100 watt per meter square per Kelvin, and the bulk temperature, that is the free stream temperature, is 30 degrees Celsius as shown. The heat transfer in the slabs is assumed to be one dimensional and steady. So this is very important point here, and all properties are constant. If the left extreme phase temperature T1 is measured to be 100 degrees Celsius, the right extreme phase temperature T2 in degrees Celsius is what? So we need to find this T2, surface temperature at the right side, or the right extreme surface temperature. Let's see the concept behind this problem. So we are given that it is a one-dimensional steady state heat conduction. Let's understand a one-dimensional steady state heat conduction for the plane wall. Now in this diagram, and T infinity is the free stream temperature at the extreme of this wall, or I can say the extreme of the slab, and in the beginning, that is the coordinate is x is equal to 0. In the beginning the temperature of the slab is, or I can say that this surface temperature right here is Ts1. K is the conductivity of this material, and the separation, or I can say the length of this wall is L. And this is only one dimensional steady state heat conduction equation, so we will consider equation only in x direction. Okay, so let's write the governing equation for this. So the heat diffusion governing equation can be written as d by dx. Remember, we are writing only for one dimension. Okay, so d upon dx of k into change in temperature with respect to the length of this wall, that will be equal to 0. So this differential equation can be integrated twice to obtain the general solution of this differential equation. That is, temperature as a function of length, or x I can say in x direction, is given by two constants, that is c1 into x plus c2. Now to obtain c1 and c2, we can substitute the limit from here, that at x is equal to 0, let's write here, at x is equal to 0, the temperature is Ts1, that is this surface temperature at this surface, the leftmost surface, and this is the first condition. And the second condition can be, let's write here, the second condition can be at x is equal to L, T naught will be equal to, TL will be equal to Ts2, that is the surface temperature at x is equal to L. So if you substitute these two values, means if you can find the constant from here, and if you will substitute here in this equation, we will get the temperature as a function of x is equal to Ts2 minus Ts1 into x by L plus Ts1. Okay, so this is the equation we will get. Now the heat flow rate across the wall is given by, so it is given by, so heat flow in the direction of x is equal to negative k into area, at surface area, change in temperature with respect to x, and this can also be written as Ka by L into Ts1 minus Ts2, which can further be written as Ts1 minus Ts2 divided by L upon Ka. And this L upon Ka, this is called conduction resistance and represented by R RTH. So this can be understood as below. Let's see that a diagram to understand this RTH. So this RTH can be understood as the change of temperature with respect to the flow of heat. So RTH is equal to delta T upon Q. Of course, T1 is greater than T2. So a thermal resistance, this RTH, may be associated with heat transferred by convection at a surface. Okay. So from Newton's law of cooling, heat flow Q is equal to HA into Ts minus T infinity. So Ts is the wall temperature, T infinity is the free stream temperature. A is the area and H is the heat transfer coefficient here. Okay, so this is Newton's law of cooling. And from this equation, we can write the resistance of the thermal resistance for convection is R T. Let's write convection. Convection is equal to Ts minus T infinity by Q, that is equal to 1 upon H into A. Now coming to our given problem. So there are 3 slabs, each of 1 meter length, and the leftmost slab, the temperature is given T1 is equal to 100 degrees Celsius, T2 is unknown, and the free stream temperature is also given. So it is T infinity is equal to 30 degrees Celsius. And the coefficient of heat transfer, that is also given in the problem, and that is 100 watt per meter square per Kelvin. So this is the left extreme phase and this T2 is at right extreme phase. Also the heat flow generated in the central wall, it is given as Q dot, let's write generated is equal to 10,000 watt per meter cube. This is 10,000. Also the thermal conductivity K of each wall is given as 5 watt per meter per Kelvin. Now you can pause the video at this moment and try to solve this problem using the given information and the concept explained above. Of course, at any time you can resume the video for further solution. So let's continue our solution. The heat generated in the central slab is dissipated through the left and right slab, right? Means left and right face. So we can write heat generated in the central slab is equal to heat in the left plus heat flow in the right slab. Let this be equation number 1. Now from Newton's law of cooling, we can write heat flow rate in the left slab will be equal to H into A into TSL minus T infinity. And here for this problem TSL is nothing but T1, which is also given in the problem. Now this heat flow in the left slab per unit area can be written as QL dot is equal to Q capital Q L dot is equal to H by T1 minus T infinity. Okay. Now let's write the value of H, T1 and T infinity here. We will get H given here is 100, T1 is 100 degrees Celsius and T infinity is 30. Right, so we will get this value. Heat flow rate in the left slab will be equal to per unit area, that will be equal to, if you calculate, we'll get 7,000 watt per meter square. Now for unit area, this equation number 1 can be written as, let's divide it by the area term. We will write Q heat generated in the middle slab should be equal to heat in the left slab, heat flow rate in the left slab plus heat flow rate in the right slab, and all are per unit area, because in the middle slab heat is dissipated from the left and the right slab. Okay. Now the value of heat flow generated in the middle slab is given as 10,000, and in the left slab we just calculated the value is 7,000 plus heat flow in the right slab, and so from here we can get the heat flow rate in the right slab will be equal to, or the right surface we can say is equal to 3000 watt per meter square. Now again, by using the Newton's law of cooling, we can write heat flow rate in the right surface is equal to H times T2 minus T infinity. Now from this equation we can write T2 should be equal to Q dot R by H and plus T infinity. We got the value, this value as 3000, and H we already know 100 plus T infinity is given 30. So T2 comes out to be 60 degrees Celsius. So this will be our final answer. Now let's go back to the question and write the answer properly. If the left extreme phase temperature T1 is measured to be 100 degrees Celsius, the right extreme phase temperature T2 is, just now we calculated, 60 degrees Celsius. Okay, so degree Celsius is already given. Anyway, to get the derivation and more knowledge on this topic, you can refer to the NPTEL course of Conduction and Convection Heat Transfer by Professor S.K. Soom of the Department of Mechanical Engineering, IIT Kharagpur.